Uh, our own very own Tona is going to tell us about the topology and complexity of deep computations.
Thanks, Spencer. I hope my microphone is working. If not, please just put something in the chat and I'll see. Yes, maybe that was before I started talking, so maybe we'll get a confirmation soon. Okay, so my talk is called Topology and Complexity of Deep Computations. This is joint work with Eduardo Dueñez, Jose Llovino from University of Texas, San Antonio. And here at the math department at U of T, we have Luciano Salvetti, myself, and Frank. Okay, so the purpose of this talk is for me to try to demonstrate that the asymptotic behavior of computations can be somehow studied and rigorously classified by invoking several tools in topology, in particular in set theory. I should also say this is part one of a two-part presentation. So I will defer some of the more technical details and examples to the second part, but I will try to cover the most important parts of the introduction in this part. Okay. So the first subject that I want to talk to you about is a sort of analogy between the Rosetta Stone and this, right? So there are three fields that I hope to convince you are connected and subject to the same ideas, just manifested in perhaps a different language, right? So on the one hand, we have topology, specifically the study of function spaces, which I already, I think, called CP theory, function spaces. Then on the other side, we have model theory, specifically logic and some other adjacent fields, perhaps. And finally, statistical learning. Statistical learning is a framework that encompasses most of modern machine learning, right? So it's basically using techniques from functional analysis and perhaps other applied areas of math like statistics to predict and also explain data. So in this context, it's perhaps most relevant for machine learning applications. Okay, now what are the objects of study that I want to connect for you? Well, in topology, we will be studying Rosenthal compacta. In model theory, the analog of this will be something called NIP theories, where NIP stands for non-independence property, which I shall define in a few minutes. And in statistical learning, we have the concept of probably approximately correct learnable class, which I will not define, but I will vaguely tell you what it is and why it matters. So these are the objects of study. There are also concepts associated or properties associated with these objects. And the one that I care about for Rosenthal compacta will be relative compactness. In NIP theories, this is the non-independence property. And in the context of PAC learnable class, I will be mentioning that the analog property is having a finite VC dimension, which I will also define in a bit. Right? The study of NIP theories has spanned multiple researchers, but I think it's fair to say that it was first isolated by Scheller in the 1970s, and he used it to classify different theories in wild versus tame, right? I have a couple hundred papers to read if I actually want to know in depth what this means. I'm not a model theorist. PAC learnable was introduced by so Scheller in the 70s. The PAC concept was introduced by Valiant. I think this was 1980 something, 84. The VC dimension was independently developed by, well, VNC, Vapnik and Chervonenkis in a somewhat similar context. And Rosenthal compacta, as we're studying it now, we're basically drawing inspiration or a lot of the machinery that we use from a paper from the 1970s, 1978, from Bourgain, Fremlin, and Talleyrand. And later, although I won't cover this in this part of the talk, several papers by Stevo that were later expanded by a bunch of people, but I won't mention that here, so there's no point in writing it down. 78. Okay, now that I drew this Rosetta Stone on the board, I should tell you. So what's the point of all this? So the key, yes.
Properly NIP, as in things which are not stable, but NIP.
Yes. So theories that have formulas that satisfy theories that don't have formulas that satisfy the independence property.
Yes, but so stable theories in particular don't have this.
Yes.
So, but do you mean unstable ones, or do you mean just all NIP theories? So that's what I mean by proper.
I'm not sure. I'm not sure I understand. So just theories that satisfy the NIP.
So not necessarily proper.
Yeah,
Right.
stable.
Not
Stable.
necessarily, your last word, not necessarily what?
Not necessarily what? Sorry.
Properly.
No, I just not necessarily properly NIP.
But yeah, we're interested in the properly NIP there, this is in between stable and unstable.
Yes,
But
I
the
understand.
model theorist,
It's the other fork, right? There are two forks. Unstable is the same as either not having the tree property or the independence property. And this is the other fork.
yeah,
Okay.
so that this is basically, these theories are not as good or if you like trivial as stable, but they're not wild. You can deal with the NIP theory.
Yes, okay, yeah.
Okay, so the key insight behind how we're going to connect these three areas is by realizing computations as points in a topological space, right? So the key idea is that computations are points in a type space. And this is the idea that we will use to connect these three things. Now, before I continue, maybe let me tell you a little bit about what the word computation means, because there's more than one interpretation, and there's somewhat of a paradigm shift when it comes to talking about this, right? So there is classical or traditional computer science typically deals with computations that have discrete states and a finite termination point, after which you get the output. Or you don't get an output, in which case the computation failed, right? So this is discrete states and finite termination. Right. But there are others that deal more with asymptotic behavior. Right? And these are quite gaining a lot of traction in recent years. And just to write down some examples on the wall, which of course I won't talk in any sort of depth, but in case you're interested in looking these terms up, there is physics-informed neural networks, which are systems that embed physical laws to study complex data, particularly in continuous, spatial and temporal coordinates, whatever that means. There's neural ordinary differential equations, which are systems that evolve over time through continuous transformations. And there's also the concept that people in machine learning study, which is deep equilibria. And if I had to summarize this in just one sentence, I'd say that imagine that you have a single layer that you're operating on in your machine, and you're iterating this layer over and over again until the output stabilizes within a margin of error. It doesn't change. And then you say, well, this must mean that the computation reached a sort of limit, and that's the answer. That's the answer, right? So there's a bit of a paradigm shift that arises from this, but the point is that for us, computations are asymptotic things, right? So we want to study this asymptotic behavior. And so the object of study are not just computations as functions in the classical sense, but limits of functions, right? Pointwise limits of a sequence are, say, is pointwise limit of a sequence. Right. What is this? Well, so a function f, I don't really want to specify the domain right now, but we can think that this is real valued, right? Real valued. So f is the limit, the pointwise limit. I will forget to say pointwise. I always mean, actually not always, but I generally mean pointwise limit. F is the limit of the sequence of fn's if for all x in the domain, f of x can be calculated from the limit of every point, right, of fx. So there is the first problem that we encounter. So the first problem is that if you take the pointwise limit of a sequence, the thing that you get, the function that you get, might not be in the same class as the functions that you started with, right? So pointwise limits need not stay in the same class, right? And the quickest example that I can offer is if you take polynomials, right? If you take polynomials and you define this thing right here on the interval 0, 1, say, right, then the first iterate looks like this, just the identity. The second iterate is just x squared. And as you increase n, this becomes steeper and steeper. And of course, the limit, you get something that is not just not a polynomial, it's not even continuous, right? So this is the simplest example, I think, of this situation. So how do we address this? Well, it's quite simple. So to address this, consider Cpx, and this will just be the set of all functions real valued on x. X will be a nice space. Typically, it will be separable and completely metrizable, sometimes even compact. Just all the functions from x to r that are continuous. And this is a topological space. And the topology that I want to use is the pointwise convergence with pointwise convergence. Topology, which is the one inherited from the Tikhonov product, right? From the Tikhonov product Rx. In other words, a limit of points converges if and only if it converges pointwise, right? So everything makes sense. Okay, now let me define two more things that I think we already talked about this for many hours. Luciano and I presented several things about Rosenthal compacta, but anyway. So B1 will be the set of functions real valued on the same space that are limits of continuous functions, right? So there is a sequence of functions in CPX such that for all x, f of x is the limit, right? These are called bare class 1 functions. And as the name suggests, if you take a limit of things in here, they don't need to stay in there, right? Because there's a bare class 2 and so on. So this set is not closed under limits, pointwise limits. Now, the second thing that I care about is a compact space K is called a Rosenthal compactum. Rosenthal. If it is homeomorphic to a compact subspace of B1, right? B1 is also a subspace of this product space with the same topology, right? So this is, I guess the definition just says homeomorphic to, but for our sake, I can just write compact subset. Okay, let's just say if it is a compact subset. B1. Okay, now there are two remarks that I think are important about the two definitions that I just wrote down that might be relevant. So there are two facts that are true about these spaces or these objects. The first one is that bare class 1 functions are not that far from being continuous. They might not be continuous. As I said, this is an example of a bare class 1 function that's not continuous, right? But bare class 1 functions are continuous on a large set. As in this example, there's only one point where the discontinuity fails. So you can't do this everywhere because it would, you can't make things that become too wild in this sense. So they're continuous on a co-meager set, which is a notion of largeness in topology, right? Now, the second thing that I want to mention that is important, there's a reason why after writing down this problem, I want to define bare class 1, right? First of all, bare class 1, this set will capture all of the limits of continuous functions by definition. But there's something else that's important, and that's that Rosenthal compacta are Frechet Urison. Which means that unlike, okay, this just means that points of closure are limit points of sequences in the space. And this already suggests the next problem that I encounter if I want to deal with this. So the second problem is that, actually, sorry, before I write down this problem, let me just say why I care about this, right? So for us, we will typically care about taking continuous functions in a space, typically a countable set of computations. We want to study the closure of the set. I have a set of computations, and I want to see all the things that are close, topologically close to the set. We want to study deep computations. And every time I use this overline, I mean the closure in the big space, right? So this is the closure of gamma in whatever general space I'm thinking about, right? Okay, now I can mention the second problem that arises from this definition. And that is that the closure of just a set of functions, if you take a point here, it doesn't necessarily mean that that point is going to be the limit of a sequence, pointwise limit of a sequence, right? That is pretty well known in function spaces, but I guess in other topological spaces like the reals, you never have this problem, right? If you have something in the closure of a set of reals, well, you can always approximate it by points inside the set. This doesn't happen here, right? So points of closure need not be pointwise limits of objects in a set, of a sequence of things inside the set, right? In other words, in general, if you have a set of functions, and you can even ask for all of them to be continuous, it is possible. It is possible that when I take the closure, this is no longer contained in V1, right? Let me just write down a very quick example with no proofs in case you haven't seen this before. So for example, if you take projections from the Cantor set into the space 0, 1, the discrete space 0, 1, right, projections, these are obviously continuous, right? So you can collect them all inside a set. And these are all continuous functions on the Cantor space. Then the closure of the set is completely outside Bear class 1. Right? The closure of the set is actually very large. So the closure of the set, if you remove the obvious things that are limits already, so the points that are already in gamma, those can be approximated by themselves, by a constant sequence, right? So if you remove the trivial case, then this is horrible, right? This is I think this is disjoint from Bear class 1. In other words, there are examples where you take the closure and you cannot approximate anything. Right? This is also a well-known example. I believe this closure is homeomorphic to beta n, right? Okay. There's also a well-known result by Rosenthal that gives precision to the sentence, this is the worst thing that could happen. But I think let's not deviate from what I was trying to do. Okay, so let me introduce a new piece of notation so that I can talk about what comes next. So notation. I won't actually use this notation very much. It's just so that I can paint a nice picture. So you take a set of real valued functions on a space. By the way, maybe I should do this before because I was kind of sloppy when I wrote down x. So from now on, x is separable, completely metrizable. And you should separable. What did I write? Oh, okay.
I was just wondering why you don't say this for.
I don't know. It's just it's a polar space. I think maybe these terms are more general, well known outside of this context. Yes. X is a polar space. You should be thinking the reals or sequences, infinite sequences of natural numbers, the Cantor space, and R to the omega and stuff like that. Okay, so now let me introduce this notation and maybe attempt to paint a nice picture for you. So if you have a set of real valued functions on this nice space and some fixed real number a, then x less than or equal to a to the power a will be the following. So actually, I'll try to paint the picture first. So this is the idea. You have a space x, right? And you're defining not necessarily continuous, but I guess for most applications this will be continuous functions on this space, right? So you can imagine this like a sort of blanket floating on top of the space or something. I like to think about colors a lot. So you have a space, and the function could be assigning shades of gray to the space, right? And then you have this like literally a picture, right? That's literally what a picture is. So what I want to do is everything below the threshold A, everything that's darker than the shade A, I want to highlight it, right? And if you have a family of these functions, well, maybe you have a lot of different pictures. So I just want to intersect those sets that I highlighted. In other words, I want to see the points that all the functions think belong below A, if that makes sense. Right? So this is just this. You take all the functions inside your set, and everything that the function thinks belongs below A, you take it together, right? So this is literally just, if I want to write this out, it's the same as this, right? So every function in your set thinks that this is below A, right? Now the reason I want to do this is because I want to state a theorem. Okay. Okay, so this is a theorem from Bourgain-Frem and Talleyrand, 78, and it will help us resolve this situation where the closure has points that are not easily approximated in terms of computation. Right? The next step will be to translate this theorem into the concrete context of computations. Right? But let me state the theorem first. So given Polish space X, given A, CPX, pointwise bounded. Now, pointwise bounded, I think probably means what you think it means. Every function in A, for all f in A, this is bounded by some number at every point. And the way to think about this in my example with the colors, the colors are presumably picked out from a finite range, right? You cannot have like a trillion different numbers to assign for colors. In computers, it's typical to use numbers from 0 to 255 to describe a color. Although I guess that would be discrete, so maybe that's not the best example, but just think that you can interpolate between different shades of red or whatever, right? So that's what pointwise bounded means, and once I write down the rest, you will see that you cannot really remove that. Pointwise bounded, following pointwise bounded. Equivalent. So the following are equivalent. If you take A and find its closure, this is contained in functions, Baire class 1 functions. Right, so this is typically called relative compactness, which I wrote in the Rosetta Stone that I already erased. this property is called relative compactness. Now, maybe I should just mention that relative compactness means something more general than this. It just means that the closure is compact. But in this context, these can be shown to be equivalent. And this, I think, is really how one should think about this theorem anyway. So you can just take this to be the definition. So this is the desirable case, right? This is when all of our deep computations are approximable by things by continuous functions, right? And yeah, not just continuous functions, but things that we already have, right? So what is this equivalent to? For all sequences in A, every time you take a sequence in A and two numbers A and B, some threshold values, then you can find finite disjoint sets of indices. Okay, I just realized I think there's a small mistake here, but I'll deal with that later. Finite disjoint sets such that what? The thing I just defined, right? If you take everything that the functions think is below A, but only at these indices. Okay. Let me just write this like this. So fi let's just collect the functions that are inside this index set. And then you intersect it with everything that's above B, right? So if you think about the picture again, you have the threshold A and the threshold B, and you want to eliminate everything that's below A and everything that's above B, right? You're trying to separate these two things. So this is empty. There's no point in the space that satisfies these things. Sorry, f of n. And this is what we call, in this context, the non-independence property. And since this is a set theory seminar, maybe I'll try to connect this with an idea that you definitely heard before. So recall that F is an independent family. If for all what? You want to select some with a yes, and you want to select some with a no, and then you want to be able to find a point that satisfies all of that, right? Independent, and this is the negation of that, the non-independence property. Okay, so I guess just write something like this. Right, the intersection of all of these sets B in A. Complement. Right? So this is, I think, hope I wrote that correctly. So that's the definition of an independent family of sets. And this is just the negation of that, but in a slightly different context. Now, one thing that I think is important to mention is that this is sort of a discrete version of that, because you can either be inside the set or not. But this is a little more subtle, right? This is like the continuous analog of that, because you can assign different values. So I want you to maybe spend a minute or two thinking about what would happen to this theorem if I replace the codomain of all of those functions, which are real valued, instead of R, if I just substitute that for the values 0 and 1. You get something that's awfully similar to this, even if the theorem doesn't make sense anymore because of the continuity conditions and stuff like that. Okay, now I want to stop here for like a minute or two. I was thinking, This is such a fundamental result in the work that we're doing and the things that we're studying. So I try to come up with an analogy to explain why this result should be true or what the NIP means in this context. And you might think it's a bit silly, but this is the best example that I could come up with of a real life situation. So are you ready? If I had left my house this morning without my jacket, I would have died. And you might say, well, that's silly. Why would you leave without your jacket if it's really cold? It was really cold in the night, like -20 or something. And to that I might reply, well, it is cold. It was cold then, but I don't know if that means it's going to be cold now. And of course, you'll say you do know because the temperature then and the temperature now are dependent events. Think about it. The set x can be something like planet Earth. And then a continuous function, a real valued continuous function that is also going to form a pointwise bounded set would be measure the temperature at each point over a period of time. And then over this period of time, collect all of those measurements into your set A. Those are all continuous functions, right? As dictated by the laws of thermodynamics or whatever. It's pointwise bounded because you don't have like a trillion degrees anywhere. And there are patterns in temperature that are impossible. And this is what this condition number 2 is saying, right? You challenge with a threshold difference AB, and I must be able to produce a pattern that doesn't occur anywhere on Earth. That's what it means for that intersection to be empty, right? And that has to be true if your system is constrained by rules, right? If temperature is governed by physical laws, then you can't encode arbitrary patterns into it, right? So one example would be, very abrupt variations in temperature over a short amount of time. That just doesn't happen, right? So that's when we're still in a desirable case, and the theorem tells us that in that case we have this nice relative compactness property. Okay, now let me finish this picture of the Rosetta Stone by connecting this to the other areas that I promised I would connect this to. And to do that, I need to, I think, define a couple more things. Okay, so this is the non-independence property in the context of, if you will, continuous logic or real valued logic. What is this property? What does it mean in the context of statistical learning? I think I also drew a sort of bridge with this and other well-known notions in set theory. So in statistical learning, there's this concept of shattering, right? So a family of sets shatters a set T if the following happens. If you take any subset of your set that is being shattered, then this can be written as that set intersected with some member of the family. Every subset of T can be picked out by the family. I'll give you an example in a second. Now, something that I just want to briefly mention is that if this happens for arbitrarily large sets, maybe you have a family of sets that shatters any sets of any size. In that case, this thing right here, this family of sets, the trace, grows exponentially because it is the power set of some set that grows in size, right? So what happens if this doesn't happen? If it doesn't shatter arbitrarily large sets? So let me just offer a quick example that I think helps clarify this. So this is just something that I lifted off of Wikipedia, which I think is a really good example. So disks in R2, if you take closed disks in R2 as a family of sets, what kind of sets can you shatter? Well, you can certainly shatter a single point because you can either select it or ignore it. And you can do that with a disk, just placing it somewhere. You can do the same with up to 3 points. Any subset, any subcollection of these 3 points, you can pick out with a disk, right? But there are sets that you cannot shatter. So for example, this set right here. This set right here has forbidden patterns. You cannot pick out these two and ignore these two with a disk because the geometry of the disk prevents you from doing that. So there are restrictions to the system, right? There's a bound on the complexity of the family. So the VC dimension, which I mentioned before, is the largest size of a set that you shatter, right? Let me write this nicely. Okay, I think I can probably just continue here. Right, so the VC dimension of a family is the largest size of a set that the family shatters, right? So F shatters the finite set T. So in this example, this has dimension 3 because you cannot shatter sets of size 4, right? Okay, now I mentioned this probably approximately correct learnable class. There's something called the fundamental theorem of statistical learning, and it says that a class, a concept class, whatever that means, is learnable if and only if it has finite dimension, right? So this has some strong implications in statistical learning that I think I don't have to go any deeper because this is the connecting concept. Okay. Right. What happens if you have a finite VC dimension? That means that after a while, the sets that you're trying to shatter get so large that you don't shatter them anymore, right? When they go beyond the size of the dimension. And then it's not a trivial fact, but not too hard to see either, that the trace that I mentioned, that in this other case grows exponentially, will actually grow polynomially in the size of the set. And that's known as the Sauer-Schella lemma. Right. Okay, so right. How do I okay, I think okay, let me just continue with the next field. So in model theory, I want to be a little bit informal just so that I don't have to write down a whole lot of definitions, but in model theory there is a concept, similar concept to this, that you will see is exactly the same, right? They are equivalent. So in model theory, let's say that you have a formula in a model M, then the formula shatters a finite set or just a set A if the following happens. For any subset of A, for any arbitrary choice of the elements of A, you can find a parameter inside the model that satisfies that the model believes that the formula is true, PS, if and only if the first half of the formula is contained in S, right? So sorry, the parameters. Actually, no, this is just like this. Right. So let me just give you 2 examples of this, and I haven't given any examples of something that is independent, and I think that's important before I move on to the next thing. Right. Sorry, I said I would address this later, but I'm already erasing it. There's a slight, not error here, because these conditions are equivalent on compact sets, but the way that the actual theorem is phrased is not with finite sets of indices, but infinite ones. But you can show the equivalence in the case where the space is compact, and otherwise you don't get this nice comparison. It's not that bad. Okay, so let me give you just a quick example of something that has the NIP in the sense of model theory and the IP in the sense of model theory, right? So example. In the theory of dense linear orders with no endpoints, this formula has the non-independence property, right? And this is not hard to see. Actually, it has VC dimension 1, right? Right. So the way to explain this would be that if you take these sets, right? Remember that the right part of the formula is being fixed by some parameter in the model, and then you want to pick out a subset that satisfies the other half of the formula. So in this case, you're fixing some parameter A and looking at everything that's less than or equal to A, right? So this collection shatters singleton sets, right? If you have a rational number and you want to fully describe it using this formula, well, if you want to include it, then just pick anything that's above it or even itself. And if you want to exclude it, just pick something smaller, and then it doesn't satisfy the formula, right? But you cannot do this for 2 points. If you have 2 rational numbers, there are forbidden patterns. You cannot include this one and exclude that one, because if you want to include this one in the formula, then this one by transitivity will satisfy it too, right? So this theory has the non-independence property. Now, let me just offer one quick example of something that does have the independence property. And with that, I think I will have connected, hopefully connected all 3 areas under this concept. Okay, so in the theory of arithmetic, you take the positive integers with the divisibility, and then of course the formula that we want to look at is just x divides y. Then this formula does encode arbitrary things, sets. It can shatter sets of arbitrary size, and it's not too difficult to see why. Just take the set of the first k prime numbers. This can get arbitrarily large because there's infinitely many of them, right? And then for any subset of A, you can just take this witness, right? You multiply the primes in S, and then this number is divided precisely by the primes in S, but nothing else, because it's literally a product of primes, right? Now, as I said earlier, I'm not a model theorist, but I believe that the fact that this theory has the independence property is strongly related to this, Gödel's incompleteness theorem. The fact that this theory is wild in a way, right? You can encode arbitrary subsets of A.
This example fails the other fork as well, right? I mean, it's not simple. Not sure.
But it does satisfy the IP.
No, I don't, but no, never mind. Yes, you're right.
Right. I don't know if you need something else to draw this connection that I vaguely mentioned with yeah.
For us, that stability is equal to not having the independence property and not having the tree property, which is the same as being simple.
Okay.
Yeah, so your example, I think, is not simple, this one.
Hmm. I'm not sure. Yeah.
So the random graph, by the way, is an example which has independence code.
Yes.
Is simple.
Okay. Okay. Yeah. I also like the example of the random graph, right? It has this. There was a clever name. I once heard a clever name for this property that you can pick a vertex and any subset, any finite subset, you can make them all adjacent, and the other set all non-adjacent. I forgot what it is. Okay. So I think this finishes hopefully the picture of the Rosetta Stone I wanted to draw. Okay, so now to the actual subject at hand. I'm going to define to you what a compositional computation structure is. So we have the following. L is a topological space. The elements are called states. And then we have P, which is a countable subset of real valued functions on L. Countable. Doesn't have to be countable, but I think for all our purposes, we assume it is countable. And it does make some things simpler, which I will mention in a bit. Countable, and the elements are called predicates. And finally, I have a subset of continuous functions on R to the P. Continuous. And these are called computations. Right. So when P is countable, R to the P is metrizable. It's a nice space. Let me see if this is how I want to define this. Oh, sorry, this is supposed to be L to the L. Right, a computation changes from one state to another. Now, here's something that's interesting. So for a fixed state V, you can define the type of V, right? This is called the type. And what you do is you evaluate every predicate on the state, right? A predicate is like a true false value, but in this case it's a real value, and you ask it, do you have this property or not? So this is just PV like this.
To be held, you still just have the pointwise topology.
Yes. What is a type in model theory? Again, I'm not a model theorist, so if I'm wrong, just let me know. What I understand a type is, it's a description of an object, right? It's a set of formulas that are true for the object. And so I think the idea is that once that list gets long enough, eventually the properties that you start writing down are no longer directly dependent on the object, but you can actually derive them from other formulas that you wrote before. There's only so many things that you can say about a mathematical object before things start to repeat, right? You can derive property number 2000 from maybe the first 100 or something. That's the art of classifying an object, right? What's the shortest list you can find that fully tells you everything there is to know about the object? So that's the idea here. This is just a list of all the predicates. So in a way, this contains all the information, everything there is to know about the state V is just captured by its type. And I think that's a pretty typical thing to do in model theory, where you just look at the space of types. Right. So this this thing right here is contained in RP. In other words, we can assume that L itself is contained in R to the P. Right? There's a copy of L inside R to the P given by the types. And if we ignore the states themselves and just focus on the types, we can assume, we can say, maybe in quotations, that L is contained in R to the P, or it's just the image of L under the type function. And with this, we define L as a closure. Closure L in R to the P. So this closure will contain things that are types that maybe no longer describe concrete states, right? It includes more stuff. Now, something else that I would rather not write down, but should also be said, is that the set of computations does require some sort of algebraic structure for it to be useful. Not to apply the topological theorems, I think it's not that important. But when you perform a computation and then another computation, you do want that action to constitute another computation, right? So you do want to have some sort of composition structure on the computations. And as we'll see in the examples that I will show you in a few minutes, L can be a nice topological space, like say the complex numbers, right? And then you're performing a computation on it that tries, for example, to approximate the roots of some polynomial defined on the complex numbers. And the idea is that if your approximation is sensible, once you iterate it over and over again, eventually you get the result that you wanted. So this set of computations can be very simple. It can be just described by a single iteration that you perform over and over again, right?
So let me ask you about your type.
Yes.
So it seems to me that what you're defining there is the realized types. But wouldn't the types simply be the functions or some class of functions from your predicates to R? And some of those would be realized in L and others would not.
Right. So the set of all of these images are the realized types, and the ones in the closure that are not included would be the unrealized types. Yes. Possibly the ones that are here but not in L. Okay. So right, I forgot to mention that this definition was introduced by Alva, Dueñez, Iovino, and Walton, 2024. Published, I think, very, very recently. Okay, so here's the next problem. And if my numbering is correct, this should be problem 3. And that is that generally we prefer having compact spaces to do things, right? Especially when we're talking about approximating and sequences and limits, compactness comes in handy, and it's a useful hypothesis for many of the theorems that we want to use. But to address this situation, what we're going to do is we're going to split the space into compact pieces and study those pieces as opposed to the space itself, right? So compactness. And to do that, I will introduce the concept of a shard. So a sizer let me just add one more thing. So when you have those things, this structure that I just defined, so LP and the computations is called the CCS, right? That's the central object of study in the extended context of what we're trying to do. So a sizer is just a set of positive real numbers that are indexed by the predicates. And the reason why we want this is so that we can define what a shard is. So a shard is just if you take L and you look at the product of the bounds given by the sizer, this is a compact space. This is the product of intervals, so it's compact, and when you intersect it with this, you get a compact space. So this is the shard given by the sizer. In other words, we're splitting the big space L into smaller pieces so that we can study the individual compact components and apply what we know about compactness in this context.
So, no, you typically says that what you do with R, and that interval is what?
Comes from this fake inclusion or identification that's
Identify elevated types.
Oh, yeah, okay, all right. So
Yes.
Two elements in L can have the same type, right? So I think that it's not a homeomorphism.
Mhm.
That what, every element has a unique type.
Yes, yes.
Yeah, yeah. Right, yes.
Given the sizer, so it looks like an abstract type, but types have to be consistent. So where does that, you know, there's some analog that you can't just take arbitrary.
Analog in what sense?
Well, here, I mean, in model theory, types, you know, are the consistent types.
Or is it some kind of theorem that everything in the closure can somehow be realized? And so,
Well, things in closure are not realized, they are the unrealized types.
yeah, but why are they consistent?
Why are they consistent?
there's no structure. You haven't said anything about what consistent means.
Oh, yeah.
So,
Potentially realizable.
yeah,
It's
yeah.
some elementary extension in which it's real.
Yeah. So you need to expand the space of states, right?
Right, but it's okay, is that a theorem?
But
Can
then
we do that? Can everything in the
I don't
closure
know.
be, that's what I'm asking, can everything in the closure be realized? My question.
It seems way too abstract to expect anything like that.
Okay.
Need more restrictions.
So if it cannot be realized, it's not a type. Yeah.
Well, it's unrealized type.
But every type can be realized, even the unrealized ones.
In
And
some
if it can-
elementary.
Yeah, right, and so I'm asking, is that a theorem? If it's not, then you shouldn't call them types.
Couldn't you just use the closure as your like extension? Like
Uh,
everything's embedded there now, all your types are realized through that. I don't know anything about set theory, so.
so that's,
The main point is that it turns out, like the theorems that we're getting from Telegraph, that you can approximate these unrealized types by actual sequence from the realized one. That gives you some handle on the.
Well, that's the theorem, and that's not true for everything, it's just, I mean, that theorem just gives you the existence of some points that can be approximated by the sequence. So.
Let's let Tona keep going.
Okay.
Yeah, I'm not sure about the abstract analogs of this to more model theoretic concepts. I think the structure I wrote down is enough to get the theorems that we want to present, because they're more Yeah, they're more topological in nature, but I'll think about the other.
Everything in the closure is realized in an ultra power of the structure. Okay.
Yeah.
That's okay.
Oh, okay.
So that's an elementary extension, okay?
Yeah,
So that's,
yeah.
that was my question.
Yes, yeah, all right.
Go ahead.
Okay. Right. So we have this set of computations. I already mentioned that the closure of the set gamma is what we call deep computations. And using I already erased it, but the Bourgain-Fremlin-Talagrand theorem, we want to characterize those sets for those spaces of computations for which the closure is relatively, sorry, the set of computations that are relatively compact in Baire class 1. Because those we can approximate by an actual sequence of functions, right? An actual sequence of things inside the set. Okay. Right, so similarly, here we don't need any identification, it's just the actual set, right? And these are called shards, these are called type shards. But the idea remains the same, right? We want to study the compact pieces of our space and see what we can do with this. Okay, now let me just mention one more thing, and then we can go to the example. Right, so for example, one reason that one would care about compactness in this context is that we want to be able to approximate things when restricted on a shard, a continuous function, by, say, polynomials, right? And this will be a consequence of the Stone-Weierstrass theorem, that if you have one of these objects and you restrict it to a shard, you can approximate it by polynomials. And this, in an abstract sense, will tell us that these objects are definable. How is this connected to the context of computation again? So there's a model theoretic explanation for this, which I will not attempt to replicate, but in the context of computations, the whole architecture of computers is designed for a certain type of arithmetic, right? You can compute addition and multiplication, among other things. So in the context of computation, I think it makes perfect sense to consider polynomials like the primitive object, right? The primitive thing that you're trying to calculate. Right, so for example, if gamma is a computation, so a function from L to L, then what happens? Might you have to say something before this? Right.
You said
Yes.
you're using the Stone-Weierstrass theorems. Do the computations form some kind of algebra, like Weierstrass?
I don't think you need any algebraic structure on the set of computations beforehand.
Stone-Weierstrass theorem usually requires something. It has to be an algebra which separates points and whatever, right? To apply it.
Yeah,
Yes.
polynomials have these properties. Yeah,
Yes, yes,
polynomials.
yes.
You have the primitives, which you know how to compute, and then you're looking at what you can compute from that using those computations.
Okay.
Okay, so let me rewrite this in a slightly different context. Okay, so we're studying functions from L to L. what happens if one of these functions can be extended to the whole closure of the space? So the fancy L, right? Extension from L to L. In other words, the restriction of L to L is exactly F, right? So under these circumstances, when you have a function that does this, if you restrict yourself to these type shards, sorry, the ones I defined up here, you have a continuous function on a compact set, and the polynomials separate points, so you can invoke Stone-Weierstrass to approximate these things by polynomials, right? That's vaguely the idea. I just realized that I'm running out of time. And if you're able to do this, there is a form in which the converse also holds. So if you have a function of this style from fancy L to fancy L, such that its restriction to any arbitrary, where did I write it, type shard can be approximated by polynomials, then the function that you started with f from L to L needs to have a continuous extension, right? So anyway, the reason I'm saying this is because there's a crucial assumption that we have to make in order to continue with this. Right, so this is called the extendability axiom, and it says the following. Sorry, I'm going a little faster than intended. So for gamma, right, so fix a CCS structure. So L, P, CCS, then we say that such a structure satisfies the extendability axiom if every time you have a computation, there is an extension from, so this is a function from L to L, so you want to find one that is bigger, right? So instead of considering L, you want to consider this. So the union of all the shards, basically. All the type shards. All of whose restrictions are continuous, right? Such that for every R sizer, when you restrict this function, you get a continuous function, right? So this is from L to this specific size, and you might have to adjust the size of this one, although there's an assumption to deal with that too. Continuous. Right, so I won't actually have time to explain the relevance of the extendability axiom, because I won't state the actual theorem that we will use this for, but hopefully the discussion about the ability to extend these functions continuously and what it means for them being approximable by polynomials, right, helps motivate this.
So what's the connection between R dot and S dot? I mean, for all R dot, there is an S dot. Is it somehow a subset? I mean, is there some kind, how are they related?
I think in principle, like, yeah, a priori there doesn't need to be, I'm not imposing any relation on them as part of the axiom.
It means you have to take a bigger compact set.
Yeah, so there's no guarantee that when you take the image of a shard that you get exactly another shard. So this will be a compact set and you just fit it inside a possibly larger compact set. So I guess the relationship between that would be that if you take the continuous image of this shard, the one that you find will contain whatever compact image you have. But they don't have to be contained, or they don't have to have any sort of direct relation, because you don't necessarily know what the function is doing.
Let me just throw in a remark. I had a lot of trouble with this axiom until Jose convinced me that this could just as easily be called the definability axiom. It amounts to saying that these computations that you're talking about are definable.
Yes, yes, I was hoping I'd have more time to in detail explain the equivalence that I waved my hands around. But yeah, this is a crucial assumption that we will make for the subsequent theorems. Now, I wonder if it's possible to get the projector
Yes.
just for the final images. So I do have an illustrative example of a compositional computation structure. And in it, let me just remind you, maybe I can do it on this side. So, you know, the camera is on this side, so I should use this side. Okay, let me just quickly remind you about Newton's root approximation theorem. Sorry, method. And the idea is quite simple. You have a polynomial like this one, right? Cubic polynomial. This one has 3 roots in the complex plane, the cubic roots of unity. This polynomial looks something like this. And the idea is that at each point of the iteration, you take a point. Sorry, that's not the correct drawing. You take a point, you find its derivative, and then you cross the point at which they intersect. This point is the new point in the iteration. So if you started at x0, then this is the next stage. Right? Now, Newton's theorem says that for most points on the plane, if your guess is good enough, eventually this will converge to an actual root of the polynomial. Now, this is just a slice of real numbers, but in the complex plane, you have more, well, complicated behavior because you have 3 roots. So it isn't immediately obvious which of the roots it will approach. Yes, 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 ready. So what I will do is I will draw the complex plane, and each point I will measure the distance of that point to the 3 roots that I already know what they are because I cheated, right? And then based on that distance, I will color the points, right? So the roots themselves will have red, green, blue colors, which should appear in a few seconds. And every other point that has a, certain things, another distance to these 3 roots will have a combination of those 3 colors, right? So here you can see green. Thank you so much. That sounds good. Thanks. Right. So here you have these 3 colors: red, green, blue. And what happens if you iterate the method? Well, at first it just looks like that, and the center, the origin, is just equidistant to the 3 roots, so it's obviously like a weird shade of gray. Thanks. And if you iterate the method, well, the points start to cluster and approach the roots, right? So after one iteration, you get this sort of weird behavior. Now, I know maybe you can't see it very well, but if you imagine the real axis cutting through in the middle, it has this situation where this point might get shot to the other side of the root, right? They don't follow the shortest path. So let me just iterate this a couple more times, and maybe you've seen this picture before. By the way, it looks blurred because all of these functions are continuous, right? So if you move slightly, ever so slightly on the complex plane, the colors should also vary little. That's what continuity means, right? That's how it looks. But of course, the limit, you get a sharp image. And I think this is a really nice example of a bare class 1 function that is not continuous. This one is not continuous because you have abrupt changes in color. It's actually almost like piecewise constant or something like that. Now, to be fair, the structure on which this is defined isn't exactly the complex numbers because there's plenty of points for which the method doesn't converge. For example, the point that has a derivative of 0, it's not clear what I should do with that. So it just like shoots off to infinity or something, right? You can obviously formalize this without too much trouble. And the set of points for which the method converges always forms a co-Meagher set. So this is actually not that problematic. This is known as Newton's fractal, but I think Newton didn't actually know about this, interestingly. I mean, he knew about the method, right? But maybe he lacked the computational tools to just create this quickly. So here's another example of another cubic polynomial. And this one has an interesting property compared to the last one, that there will be open regions in this one where the method fails. And you can kind of see them because they never attain a single color, right? These open blobs, if you actually zoom in, you can see that it's like weirdly pixelated because even after many iterations, the computer doesn't really know what's happening. If you were to zoom in, this would look like a sort of white noise. I mean, not white noise, like a colored noise, right? I guess. Right. Okay, so stay tuned for part 2 of this talk where I deferred some of the technical details, hopefully the application of the extendability axiom, and how we actually use the BFT theorem that I mentioned to connect these with real computations. And if you want to have a look, you can also find the paper, the preprint of the paper there. Thank you very much.